I've got a very, 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 very large magnetic field. Okay? Very large magnetic field. Spins whole dang long ways. Okay? It is uniform throughout. Let's draw it going into the board. Or for you, it would be down into your desk, down into the paper, for how you're drawing. So to get it relative to what I'm doing in my direction, you'll have to pick your paper up and hold it like the board is. And then I'm going to put, just like I did here, a charge. Let's do, if you will, an alpha particle. An alpha particle is shot in at a velocity of, I don't know, let's use 5.9 times 10 to the 6th meters per second. That's pretty quick. All right? I want to kind of go through a few thoughts here. I want to give you a magnetic field strength. Let's go with another small one. Let's go with 6.7 microtesla. 6.7 microtesla. Okay. What force is this alpha particle going to experience? What force is this alpha particle going to experience, and what's the direction? What's the direction of this thing? Okay. So F equals Q, B, Q, V. Do I need the sine theta on there? No, because it's 9 degrees, sine of 90 is 1. I can just drop it. So let's plug choke through this real fast. F is going to equal B, which I told you was what? 6.7. -6. What's the charge of an alpha particle? Not -2. +2. What is an alpha particle? Helium nucleus. Helium nucleus. How many protons? 2. How many neutrons? 2. 2 protons, 2 neutrons inside of the helium nucleus. If you look up there at the periodic table, atomic number of 2, atomic mass of 4. Right? So that's an alpha particle. That means 2 protons. The charge here is 2 times the charge of a proton, 1.6 10 to the negative 19th, right? 2 times that, times its velocity, 5.9, 10 to the 6th. What force is this guy going to experience? What force is this guy going to experience, please? .36, 26, 10 to the negative 17 newtons. Now, come back and get a direction for this guy. Left-hand rule. Right? What directions am I going to have? Everybody, left hands. So, magnetic field goes in. Alpha particle goes to the right. An alpha particle is positively charged. We don't have to reverse this. Which way is the force? Up. All right, so this is going up. Now, I need you to have a realization here. I've got a force acting upwards on this particle. What path is that going to make this particle take? Yeah, it's going to curve upwards, right? I'm going to get something like this going on, right? It's going to curve upwards. There's a force accelerating it upwards, and so it's going to curve upwards. Now, let's repeat this process, just out of curiosity here. Now, my alpha particle is right here. it's still in the magnetic field, right? It's still in the magnetic field. It's still going perpendicular, right? It's still going perpendicular to it. It's going in, the magnetic field's going in, it's going in a plane next to it. Thus, it's still going in a perpendicular manner. Thus, looking at the math here, QVB, assuming that the acceleration is accelerating it this way, the velocity really isn't going to, the tangential velocity, I'm already giving away my hand right now, the tangential velocity really isn't going to change. So the magnitude of the force right here is still going to be the same as what we calculated down there. Yes? The direction is going to change though. Where's the direction of the force now? Use left-hand rule, right? The velocity now is going like this, right? It's pulled it all the way around to where it was going straight up. So, into the blur, right? Particle's velocity is going up, which was the force. To the left. Alright, so now I got a force going like this. That's going that's nice. So I have a force going up, I have a force going to the left. This force is going to cause the particle to do what? Surge forward, right? Ah, yes. So we're up in the top right now. Alpha particle, I apologize for my poor drawings. Same velocity going now to the left. Left-hand rule, which way is the particle going to go? Well, velocity is going like that, in, force is coming down. So path is going to be back around. You see what's happening here? Yeah, we have, at all points in this circle, alpha particle, we have an inwards pointing force, and the force is constant. An inwards pointing force of the thing going in the circle. What does this scream? Centripetal force, right? Particles that are allowed, if the magnetic field is big enough, the particle going through it will always loop back around on top of itself. It will make a certain centripetal force here, which means I can come down here and calculate the radius of this circle. How far around is it? What's the radius of this circle? How big of a circle do we have here? So sum of the centripetal forces equals mv squared over r. mv squared over r. Okay? And in this mass that we're dealing with, the thing going in the circle is the alpha particle. Yeah? Okay? What force is supplying the centripetal force? What force is pointing inwards?
This thing first.
Yeah, this magnetic force, right? I'll call it Fm for magnetic. M alpha v squared over r. We have an equation for that, right? This is QVB equals M of alpha v squared over r. Yeah? We're tracking with me so far?
Yeah.
Now, thankfully, we already calculated the left-hand side. What does the left-hand side come out to be? 1.26 times 10 to the what? 17 equals. Now, mass of alpha particle. How do I get that? Good. 2 protons, 2 neutrons. So that's 2 times mass of proton is 1.673. 73. 10 to the negative 27. Plus mass of mass of 2 neutrons, right? Focus all the way over. I'm going to need as much space as I can get. Plus, I'm sorry, 1.6. 2 times 1.65 times 10 to the negative 27. Right, so this guy, 675. 2 times 1.675, so this is 2 times 1.675. Sorry for all the mix-ups, times 10 to the negative 27. All right, that's the mass, the velocity I gave you. So the velocity up here we have is 5.9 times 10 to the 6. So this is times 5.9, 10 to the 6th, right? Over, yes, thank you, v squared over r, right? Working this with just units, or just the variables, because this gets overly complicated here, you're going to end up with the radius equaling mass of your alpha particle, velocity squared, divided by that force, right? That's what the radius is going to come out to. Now you've got all the pieces of that already, so please give me that radius. Seems like we're all getting 1.8 times 10 to the 4th. Is that, I mean, please double check that for me. I'll punch it in. I'm letting you all do it. Right? So, yeah, 18,000 or 18 kilometers at that point in time. 18 kilometers. This small of force, it would take a little while to get this alpha particle to curve around. We increase the magnetic field. We can make this alpha particle turn around in 20 centimeters. No problem. No problem at all. Okay. So radius 1.8 times 10 to the 4th. Charges and magnetic fields like to go in circles. Charges and magnetic fields love to go in circles. Class.